So we're going to do a practice test here, and we're going to do some multiple choice questions because we haven't done those yet. School administrators collect data on students attending the school. Which of the following is just quantitative? A, class. That's categorical. Okay, there's no, you just pile up the number of people that are in each class. Or you take percentages of them, but you don't quantify the data. B, grade point average. That's quantitative. Okay, 91.1. The grade point average, one of the things that's indicative that it's quantitative is that it's continuous. C, whether the student is in AP classes. Again, categorical, AP classes, yes or no. Whether the student has taken the SAT, yes or no. E, none of these. Well, number one is B. Okay, grade point average, that is quantitative. 2, which of the following variables would most likely follow a normal model? Family income. Well, family income is going to be, you're going to have a whole lot of people. Let's just say this is 0, this is 1 billion. You're going to have a lot of people over here somewhere, and then down here you're going to have the people making 1 billion. Math teachers, way over here somewhere. Okay. So that's not normal. So A is out. Heights of singers in a co-ed choir. Okay, this is A. B, that heights, you're going to have, so here's some heights here. The graph is going to look like this. Heights of female students and then male students. You're going to have a bimodal distribution because you're going to have two groups of heights. Heights are normally distributed, usually, but only for the same populations. In a co-ed choir, you're going to have two populations together, male singers and female singers. So C, heights of male elephants. Okay, there you have adult male elephants. You have a very specific population, and that's more likely to be symmetric and bell-shaped and follow a normal model. D, scores on an easy test. Scores on an easy test are going to be skewed left. That is, here's 0 and here's 100. You're going to have a whole lot of people with high scores, and then very few people with low scores, so it'll be skewed to the left, skewed towards the lower numbers, not normal. So the answer to 2 is C. Weights of adult elephants, of male elephants, are a normal model. E is wrong. 3. Professors kept records on grades that students have earned in his class. He wants to examine the percentage of students. Now this one's a little tricky in the sense that if you think about it, okay, students earning A grades A, B, C, D, and F. One of the things about, first you're going to say, well, this is categorical, and the categorical is the right answer, and you would use a pie chart to represent this D. But usually with categories, it doesn't make any difference in which you order them. Like you could take, if you did a pie chart, students taking the SAT and students haven't, you could have the SAT on the left and the non-SAT on the right, or vice versa. But usually you wouldn't order A, B, C, and D, and F in any order other than that. And if you think about the grade ranges, you know, like, I don't know, 100 to 93 or whatever for an A, and then so on for B, you could think of it as a histogram because it has bins. But by calling them A, B, C, D, and F, you're making categories. So this is categorical variables. And so the answer is pie chart. All the rest of these choices, box plot, time plot, dot plot, and histogram, are visual displays for quantitative data. So the answer to 3 is D, pie chart. 4, what is true of the data shown on the histogram? The distribution is approximately symmetric. That's true. The mean and the median are approximately equal. That's true. They're both going to be right smack dab in the middle. 3, the median and the IQR summarize the data better than the mean and standard deviation. That's not true. Although the median and the IQR will summarize any distribution of quantitative data, no matter how it's distributed, if you have a symmetric and bell-shaped distribution, then you want to use the mean and standard deviation because they give you a much more nuanced description of the distribution. 5. Okay, let's see. 2 scores, 2 sections of class. Okay, here's 5. Okay, section A had 15 students, had a mean score of 80, and B had 20 students with a mean score of 90. Overall, what was the approximate mean score? This is an old math problem, and you have to weigh your answers, which means you're going to take 15 times 90. I'm sorry, 15 times 80 plus 20 times 90, and you're going to divide it by the total number of students, 35. So 15 times 80 plus 20 times 90, and divide by 35, and we'll get the calculator here. Let's clear all this off. 15 times 80 plus 20 times 90. Notice I put this in parentheses because the whole thing is the numerator. Divide by 35. Okay, and I get it's approximately equal to 85.7. So we go here and C, 85.7 is the right answer. All right. Your stats teacher tells you your score was in the 3rd quartile of the class, which is true. You got 75% of the test. No. What that means is here's 1st quartile, 2nd, and here's 3rd. Okay. You're in the 50 to 75, here's the 4th quartile, percent of the class in terms of just total numbers. Okay, so it doesn't mean you got 75% on the test. Maybe nobody got 75%. Maybe the highest, the max was 70%, and the min was a 0 or whatever. So the quartiles do not relate to actual scores on the test. So the first answer is out. 2, you can't really tell what this means without knowing standard deviation. Well, we're talking about quartiles, which relates to a box plot, although we could use quartiles with the normal distribution, but you don't need the standard deviation to know what this means. I already told you what it means. It means you are within between the 50 and 75 number of students, percentage of students in terms of scores, but you have no idea what your score is. Okay. 3, you can't tell what this means unless the class distribution is nearly normal. That's completely and totally not true. You don't need a normal distribution in order for the distribution of a box plot to work. Okay? What would you need to know? You'd need to know the median and Q3. Then you would know your grade was between 2 scores. So if the median, let's say the median so this is 50%. This is 50% of the total scores, 75% of the total scores. So let's say 10, it could be that 50%, the median was, let's say, 75, and then Q3 was 90. So you got somewhere between 75 and a 90 on the test. Or it could be, let's forget about the test, let's say it's just straight points. Let's say the median was 15 points. Let's say it was a 45-point test, and Q3, it was a really hard test, and Q3 was 20. So you got somewhere between 15 and 20 points on the test. But so what you need to know is what the median is and what Q3 is. But none of that other stuff will help you. So the answer is 6 is A, none of these. 7. Normal model describes scores in a history class. Parker has a standardized score of 2.5. Okay, what does that mean? Plus 2.5. Well, that's good for Parker. He's 2.5 standard deviations above the mean. So here's old Parker. And his Z-score is 2.5. Okay, does that mean he's 2.5 points above average? Absolutely not. He's probably way higher than that. Okay, there's no way that Z's translate into actual scores. The scores have been removed. This is a standardized performance. What this means is, if he's 2.5, is that probably 99% of the people did worse than him and about 1% did better. B, 2.5 standard deviations above for the class. That's exactly what I just said. So 2.5 sigmas has a standard deviation of 2.5. No. Z-scores and standard deviations are two entirely, totally different things. Has a z-score that is 2.5 times the average. No. Z-score is not a multiplier. E, none of the above. That's not true. We just said that B is 2.5 standard deviations above class. That's the exact definition of what a z-score is. Okay, so that was, what number was that? That was 7, 8. The advantage of making stem and leaf display instead of a dot plot is that a stem and leaf display satisfies the area principle. No, the area principle has to do with displays of categorical data. B, shows the shape of the distribution better than a dot plot. Well, that's not true. They both show the shape of a distribution. Preserves the individual data values. Well, we know that's true. The individual data values are exactly displayed on a stem and leaf display. They're not exactly displayed on a dot plot. Dot plot will show integers, and then you have to kind of guess what the values are in between the integers. D, stem and leaf display is for quantitative data, while a dot plot shows categorical data. That is completely, totally, and utterly false. They are both displays for quantitative data. E, none of these. No, we just said that the stem and leaf display preserves the individual data values. So the answer for 8 is C. 9. 5-number summary for 24 students in a statistics class. Which statement is true? There are no outliers. Well, is that true or not? IQR equals Q3 minus Q1, which means the IQR equals 18 minus 15, which is 3. 1.5 times the IQR is used to compute the outlier fence, which is going to equal 4.5. Now the right-hand fence equals Q3 plus 1.5 times the IQR, which is going to equal 18 plus 4.5, which is 22.5. So on the terms of the right-hand fence, the max 22, not an outlier. Now, Q1, the left-hand fence, equals Q1 minus 1.5 times the IQR, which is going to be 15 minus 4.5, which is 10.5. So clearly the minimum is not an outlier because it's within the fences, within the fence. So, A, there are no outliers. That is true. B, there is at least one outlier. False. C, there is at least one high outlier. False. D, there are both high and low outliers. False. E, false. The answer to 9 is A. There are no outliers in the data, and you just showed that according to our rule of thumb. 10. Which of the following summaries are changed by adding a constant to each data value? Okay. Measures of center are changed by addition, subtraction, multiplication, and division. Measures of spread are only changed by multiplication or division. Okay, so which of the following summaries are changed by adding a constant, sliding it left or sliding it right? The mean and the median. Standard deviation? No. So the answer is C, 10C, the mean and the median. Okay, moving on. Number 11, dogs and cats. Table shows whether students and electric have dogs or cats. What is the marginal distribution in percent of liking dogs? Now, liking dogs is vertical, and the marginal totals for liking dogs is at the bottom. So, yes and no, yes and no. These are the two marginal totals, and they are 304 out of 335 like dogs, and 31 out of 335 don't. And the 304 out of 335 is approximately equal to 90.7%. You just do it on your calculator. And 31 out of 35 is, as you would guess, approximately equal to 9.7%. So this is the marginal distribution in percent for liking dogs. Now, if you're going to do liking cats, you would do 215 over 335 are yes, and 120 over 335 are no. Okay, and you would express them as percents. 2, or B, that's A. This was A. B. Gotta stop writing over stuff. Okay. B. What is the conditional distribution in percent for liking dogs for students who like cats? In other words, given that you like cats, okay? Now, how many people like cats? Here's the liking cats, 215. What percentage like dogs? Okay, well, 194 out of the people that like cats like dogs. See? Yes and yes. Like dogs and like cats. So that's 194, but we're not asking how many people like dogs and like cats. We're saying, given that you like cats, okay, 4 students who like cats, what percentage like dogs? So we're going to say 194 out of 215. Okay, and that's approximately equal to 90%. Now notice that's close to the people who like dogs. Okay. All right. Now, C. What kind of displays would you do to examine the association between liking dogs and liking cats? Well, okay, you're comparing liking dogs and liking cats. So you could use, probably the best thing would be a segmented bar chart. Segmented bar charts are the best thing for this kind of table. For contingency tables. Forgot the definition myself. Okay, so for contingency tables with marginal totals. Why? Because segmented bar charts show 2 variables. But you could do side-by-side bars. Those would be also good. Or pies. Okay? All right. Do liking dogs and liking cats appear to be independent? Okay, so how are we going to answer this? Well, let's see. 90% of cat lovers like dogs, which appears to be the same as the total. Okay? Now, 64% of dog lovers, let's look at dog lovers, like dogs. Okay, yes. 304. So 194 out of 304 dog lovers like, that's 0.64, okay, 64% of dog lovers like cats, okay, which is the same as the total. and which the total is 215 out of 335. In other words, total people that like cats is 250 out of all total people 335, and that's about equal to 2.64%. So, given that you like dogs, what's the probability that you're going to like cats? Well, it's equal to the probability of all of the people together liking cats. So it appears that it doesn't make any difference whether or not you like dogs. The fact that you like cats is unaffected by whether or not you like dogs, and vice versa. The fact that you like cats appears to not affect whether or not you like dogs in terms of the numbers that we have here. So they are approximately independent. Now the numbers aren't exact, but they're close enough. Okay. House calls. 12. Okay, plumber makes house calls. She charges $30 to come out to the house and $40 per hour for services. Table shows statistics for the past month. Fill in the table to find out the cost. Now, we are multiplying and adding. Okay? So, the mean is going to be affected by both addition and multiplication. So, the mean is going to be 30 plus 40 times 4.5. Okay, that'll be the new mean. And that'll be $210. Okay, that's the new mean. Now the median is also affected by addition and multiplication. So that'll be, so this is the mean, and the median will be 30 plus 40 times 3.5, okay, which is 170. So the new median is $170. Now the standard deviation is only affected by multiplication. So the standard deviation will be 1/2 times 40. So let's see. 20% of 40. Oh, I can't do this in my head. This is embarrassing. So 1.2 times 40. Okay, so standard deviation is $48. And the IQR is going to be affected by multiplication, and so that's 2. IQR is going to equal 2 times 40, which is 80. Okay? So, to run down the numbers, the new mean is 170. No, the new mean is 210. The median is 170. The standard deviation is 48, and the IQR is 80. Now, the minimum, that's going to be affected by both operations. 0.5, 30 plus 40 times 0.5, and that's going to be $50. So the minimum is 50. $50 is the minimum. Okay. Now, here's they're trying to throw you for a loop. The past month, the time the plumber spent on one service call corresponded to a z-score of negative 150. What is the z-score of the cost of that service call? B. It is negative 150. Okay, z-scores are totally unaffected by any adjustments you make to the data. As long as you make the same adjustments to all the data, whether you add, subtract, multiply, or divide, when all is said and done, it's z equals, man, I just cannot write this right, y minus mu over sigma. So no matter how much these change, they're always going to change in the same proportion, and y is going to be changed. Everything is going to be changed, but z will be unchanged. Whenever all is said and done, as long as you make all the changes to everything properly, you only multiply the mean or the standard deviation or divide it, and you apply all operations to the mean, then you're going to end up with the same z-score. Z-score is unaffected by changes to the data as long as it's consistently applied. So the answer there is negative 1.5. You need to do no calculations if you know what you're doing. Okay. 13. Here we go. Now, healthcare or health insurance. Okay. So what do we got going on here? We have okay, first of all, they want to know, are any of these guys outliers? Okay, all right, well, we got Q3 minus Q1 is the IQR, and so that's going to be 16.7 minus 10.8, okay, which is 5.9 equals the IQR. Right-hand fence equals 1.5 times the IQR plus Q3. Okay, so the right-hand fence is going to equal 1.5 times 5.9 it's 8.85 plus 16.7 Q3. Okay, 16.7. Let me put this over here. Plus 16.7. Okay, so the right-hand fence is 25.55, and the max is 25.8. So the right-hand fence equals 25.55. So technically, if you will, 25.8 is an outlier, but just barely. And it's good to make a point that it's just barely. I mean, we're talking about a rule of thumb to begin with, okay? So we're talking about something that's just barely an outlier. Okay, it's not even 3 standard deviations away from the mean if this distribution can be described with the mean and standard deviation, which we'll find out it actually can't be. But spoiler alert. Okay. Were any of the states outliers? And clearly, the minimum is not an outlier with, the 1.5 times, I forget what that is. Oh, it's 8.85 is 1.5 times the IQR. So you subtract that from Q1, the minimum is going to be well inside of that. Okay, so we have one outlier. Now here's the history. Let's go on here. Here's the histogram of the data. Is it more appropriate to use the mean and standard deviation or to describe? Well, let's talk about the distribution. Okay, so B, the shape of the distribution of, what was it we're talking about? Okay, percent of people of the percent of uninsured in U.S. in 2002 is skewed right, higher numbers, with a gap between 23 and 25 and an outlier at 25.8%. Since the distribution is not symmetric and bell-shaped, the median and IQR must be used to describe it. All right, moving on. Veterinary costs. Costs for standard veterinary officers, $80 of mean, standard deviation of 20. Okay, so they want us to draw and clearly label the model. Okay, now I can't draw on this thing. I'm not on my iPad, so I can't draw on it. So I should have put it on the side of a document or something. Sorry about that. Anyway, A, but I will draw it here. Now, one thing that's sort of interesting to know, which I haven't mentioned to you, although they have talked about it in the book, is that the first standard deviation occurs at the inflection point. That's where the curve changes from being convex down to convex up. So that's where sigma 1 goes. And you got 2 and 3. But you got to draw the curve a lot better than I do. All right, and then here's the median. Okay. So we're going to draw and clearly label the model. So you got 80. That's mu. And then 1 sigma, 2 sigmas, 3 sigmas, and -1, -2 sigmas, and -3 sigmas. And we got 34%, 34%, 13.5%, 13.5%, 2.35, 2.35, that's between 2 and 3, and then 0.15% takes care of everything else. Okay, it's unusual to have a veterinary bill of $120. Well, here's 80. Next standard deviation is 100. Okay. And 2 standard deviations is 120. And 3 standard deviations is 140. Going the other way, it's 60, 40, and 20. All right. So 20 being 3 standard deviations to the left, and 140 being 3 to the right. Is $125 unusual? Yeah, because it's more than 2 standard deviations from the mean. So more than 2 standard deviations from the mean is unusual. Under most circumstances. Under some circumstances, we don't tolerate it, but under most we do. What is the IQR for the costs of standard deviations? Okay, let's be C, IQR of costs. Well, the IQR equals 4/3 sigmas, which equals 4/3 times 20, which is 80 over $3, which is what? 3 goes into twice, carry the 2, 8, what is it, $28.67 or something like that. Let me look at my notes here. $26. Yeah, I would trust my mental math. Okay, $26.60. Anyway, 80 over $3. Okay, that's if you remember that it's 4/3 sigmas. If you don't, then you got to do inverse norm. Well, there's a couple different ways to do it. But yeah, inverse norm on 0.25, and then inverse norm and 0.75. Use the mean and standard deviation. That'll give you the $2 amounts, and then you subtract them. I suppose that's the easiest way to do it. But the easiest way to do it is remember that the IQR is 4/3 standard deviations. In other words, negative 2/3 sigmas is the 25th percentile, and 2/3 sigmas is the 75th percentile. All right. Soda cans. A machine that fills soda cans with soda according to the normal model with mean of 12.1 and standard deviation of 0.05. Cans claim to have 12 ounces. How many are underfilled? Okay. All right, so let's draw a picture. Now we're told it's approximately normal, 12.1 and comma 0.05. All right, so here's 12.1. That's the mean. Now 12 is what they're supposed to get. Okay, so what is this percent? How many people get 12 ounces or less? We'll call it 12 ounces or less. So, well, z equals y minus mu over sigma, which equals 12 minus 12.1 divided by 0.05, which is 0.1 divided by 0.05, which the z equals 2, or negative 2, negative 0.1. It's negative 0.1, so z equals negative 2. So, if you remember from the setup of the normal curve, 2, 3. So we got 34, 13 and a half. So what's here? From here to here is 2.35%. In other words, from negative 2 sigmas to negative 3 sigmas is 2.35. Now here we are at negative 2. This is 12.1. I said that's negative 2 sigmas. And this is 0.15%. So 2.5% are to the left of negative 2 sigmas. So 2.5% don't get enough soda. Is that good or bad? Well, that's another question. Okay. So 12%, 2.5% are underfilled. Now, if you use the calculator, you'll get a slightly different number. B. Management wants that 12 ounces to become 1%. So, if the mean remains 12.1, what has to be our standard deviation? So we draw a picture, and here's 12.1, and here's 12. But now we want this to be 1%. Now, everything's the same. Okay, that is the y, our y value of 12. That's our target value. Mu has stayed the same. But now we want 12 to be more standard deviations away from 12.1. In other words, we want it to be 1%, not 2.5%. Okay, at 2.5%, it was closer in terms of standard deviations to 12.1. So we want more standard deviations between them, which means you have to make standard deviation smaller. We have to make the ruler smaller, if you will. Okay? So z equals y minus mu over sigma. We solve for sigma, and sigma equals y minus mu over z. Okay? So sigma will equal, well, it's the same thing. 12 minus 12.1, that's 0.1, over whatever the z-score, z of 0.01 is. Okay? So sigma equals 0.1 over, now we'll use inverse norm to find that z-score. In fact, we can take 0.1 and divide it by the inverse norm, second var's inverse norm of 0.01. And we get negative 0.0429. Here, let me clear that. 0.1. negative 0.1 divided by, I was forgetting my negative signs, second var's inverse norm of 0.01. Yeah, that's where I'm getting confused. Okay, so that's approximately equal to 0.043. And let's just see what the inverse norm of 0.01 is. Okay, so that's pretty small. Okay, that's, let's call that z of 0.01 is approximately equal to negative 2.33. All right. Okay, so we need a standard deviation of sigma would have to approximately equal 0.03 ounces for 1% of the soda cans to be unfilled. Okay, that's scenario 1. Scenario 2. Standard deviation remains at 0.05. What mean do we need? Okay, so I guess you saw that coming. So this is BII or whatever. Okay, so z equals y minus mu over sigma. So now we're going to change the mean. So we got sigma z equals y minus mu. Add mu to both sides. Subtract sigma z. Mu equals y minus sigma z. So the new mean will equal y, which is 12, minus sigma, which is 0.05, times the z-score, which is negative 2.33. So mu is going to equal, let's get the calculator here. Now, here's the inverse norm. We just calculated it for 0.01. So it's negative. So let's multiply this times 0.05. And then let's add it to 12. And this gives us our new mean, which is, no, that wasn't right. What the heck did I do wrong? I should have subtracted it. Let me do it the way I wrote it. Let me clear this. So 12 minus 0.05 times negative 2.33, 12.116. So mu is approximately equal to, let's call it 12.12. So ounces. So the standard deviation remains 0.05. The mean has to be 12.12 ounces for 1%. So if standard deviation remains 0.05 ounces, hold on, honey. The mean must be 12.12 ounces for 1% to get 12 ounces or less. And that's it.